Hello mathematicians, puzzlers, and other curious people. We're here in this video to look at what happens when an exponent is a fraction. So here we're considering, and let's just suppose for a moment that we got this as a last step in some other problem. We're considering what happens when x is 2 to the power 1/4. Now the idea is that we want whatever we get from this to be consistent with this other property of exponents, where if we have a base to 1 power and then raised to a further power, then the result of that would be as if that base is raised to the product of those powers. So here's what I know. I know that x to the 4th power should be the same as 2 to the 1/4 to the 4th power. Whoops, that shouldn't be an x, that should be a 4. X is on the brain. Hey, it happens. Okay, so we've got 2 to the 1/4 to the 4th power, but we know that we should be able to simplify that as 2 to the 1/4 times 4, which is just 2 to the power 1, which is just 2. So now we know that our x here, if we raise it to the 4th power, should be 2. Well, what if we just take a 4th power on both sides? Then that should give us that x is just the 4th root of 2. Now I need to point something out here. There was nothing particular about the numbers we chose, like 2 or for it to be 1/4. So it doesn't matter what our base is, it doesn't matter what unit fraction we have. So in general, if you have a base raised to the power 1 over some denominator, that's going to end up being that denominatorth root of that base. Now what about if we have a non-unit fraction, such as that base to, well, just the n over d power? Well, we can use this same property to rewrite that as the base to 1 over d times n. If you multiply these together, you would get n over d. So what that tells me is that could be the d root of that base to the power n. Now, one thing that's convenient is it would work equally well if we had put the n as the first of our the first of the two factors here. So we could instead say that that would be the dth root of b to the n, whichever way you find convenient to write it. So with these formulas, now we have that anything we can do with an exponent is also true about a root. For example, if you have the square root of 25x squared, we can rewrite that as an exponent. And then we can say, okay, well, exponent properties say that we can apply that exponent factor by factor. So we'd have 25 to the 1/2 times x squared to the 1/2. Well, that's just the square root of 25 and the square root of x squared. So often what we'll do is we'll just say, okay, we know that this would work. We'll just go straight from that to that and go factor by factor. And then we'd be able to say, okay, well, that's 5, and since x could have been positive or negative in the first place, 5 times the absolute value of x. So I've got some more examples, and here's one. So we're using what we know in this one about radicals, which is that radicals apply nicely to factors. So really, if we've got this factor here, 24 over 81 to the 1/2 power, and this factor here, x to the 4th to the 1/2 power, we can rewrite it this way. And then we can say, okay, well, we already know, because fractions behave nicely with radicals, that we can break it down to this. Okay, so then our question becomes, how do we break this down further and get as many radicals to just normal numbers or normal variables as we can? So let's look for the easy parts first. So I know the square root of 81 would be 9. That just popped right into my head. If it pops right into your head, go with it. That square root of 24 is a little bit harder, and one thing that can help is to factor these numbers down. There's more than one system for organizing this, but I'm just going to try making a chart of factor pairs. So that could be 1 times 24, 2 times 12, 3 times 8, or 4 times 6. And I noticed that my greatest square factor here is 4. So I'm going to rewrite this as the square root of 4 times the square root of 6. Now this x to the 4th here, if we expand that out, we see that we could make 2 equal factors, 2 equal groups like this. And one trick that people will use is they will take the power on the exponent and divide that by the root, in this case, invisible 2. And that will tell them how many factors in each group. And we don't need an absolute value for this one because it's being squared, so it's automatically going to turn positive. So we're almost done. I just noticed one more thing, this square root of 4, because remember, I picked 4 on purpose because it's the greatest square number. I can say, okay, well, that's 2. The greatest square number that appeared in factor pairs for 24, that is. And this would do for a final answer. Or if you want to condense it all into a single fraction, you could write it as 2x squared times the square root of 6 over 9. And that would do also for a final answer. And I've got one more example. So in this one, I notice we've got a radical expression and a rational exponent expression being added together. So we'll probably need to do some complicated stuff here. So the first thing I'm going to try is that same thing again of applying the radical or the exponent, whichever it is, because remember they're in a lot of ways the same thing. I'm going to try applying them factor by factor within their radicand or their base. So I'll have the cube root of 24 times the cube root of x to the 6th, and to that I'll be adding 9 to the 2/3 power times x cubed to the 2/3 power, which I know how that property is going to go, so that'll just be 2/3. And it doesn't really look any simpler than what we started with. I'll admit that. This is one of those things where sometimes it gets worse before it gets better. So I see I've got a 24 to contend with here. So I'll use a factor table for that again. So we could have 1 and 24, 2 and 12, 3 and 8, or 4 and 6. This time, instead of square numbers, I'm looking for cube numbers. So 1 cubed is 1, 2 cubed is 8, 3 cubed, so 3 times 3 times 3 is 27, and I know I'm not going to find any more than that within factors for 24. So the greatest cube factor of 24 I see is 8. So that's how I'm going to break that down. So I'll have the cube root of 8 times the cube root of 3, my other factor. Well, then I've got the cube root of 6 here. So just as or the cube root of x to the 6th, sorry, the cube root of x to the 6th. So just as a reminder, if we have x to the 6th and we're trying to make 3 equal groups out of that, they'd have 2 each, and each of those would be the cube root. So we'd say that x squared is the cube root of x to the 6th, because if we repeated that 3 times, we'd get back what we started with. So I'll just say x squared. And again, if this were larger numbers that were not convenient to write out fully, it could be very convenient to say, okay, 6 factors of x divided into 3 groups would be 2 factors of x in each group. Now we've got 9 squared to the 1/3 power. I think that it could be convenient to take this particular fractional exponent and put that in root form, and then we'd have 9 squared here. And I notice that we've got 3 times 2/3 here. Well, that's just going to be 2. We know how that works. So we just have an x squared. Okay, so it's starting to look a little simpler in some ways than it did before. Still kind of a mess. Still not what I would call a fully simplified expression I'd want to work with, but we've made progress. So one thing I notice here, 9 squared is 81. So we're taking a cube root of 81. So that leads me to believe I'm going to want a table like this, but for 81. Fortunately, there aren't that many options. It could be 1 times 81 or 3 times 27. Well, I know 81 is not a perfect cube because, again, that's 3 times 3 times 3 times 3, so not a perfect cube. So my greatest perfect cube factor here is 27. So let's go ahead and continue this breakdown. So we'll have the cube root of 27 times the cube root of 3. I've kind of run ahead a little bit here, so let's copy in the rest of the problem around it so that we're keeping ourselves organized. Not uncommon at all for mathematicians to run ahead on something like that. Okay, so here we've caught up with ourselves and brought the rest of it along. So now we can apply some of these cube roots. So I see this cube root of 8. Well, that would be 2. We know that from before. The cube root of 27, let's see, 1, 2, 3. So 3 cubed is 27. And let's bring in the rest around it. Now, a person would have some excuse at this point for thinking they were done, but they wouldn't be done. Here's something I notice. I notice that we've got a common, both a like term in terms of the variable, and also in like terms based on the radical. So we can combine those. So in all, what we would have, well, 2 plus 3 is 5. So combining like terms still works if there's a radical involved. So we've got 5 times the cube root of 3 times x squared. And this would work for a final answer, and it would be accurate for all problem-solving purposes. And there's even a sense in which this could be considered sort of a canonical form of it, because you've got all your constant factors out front. Another thing, though, that we'll often do is make it so that the radical factor is the last. So that form would be 5x squared times the cube root of 3. And that would also do for a final answer form. It just depends on whether you want to emphasize the constant factors being upfront, like a coefficient, even though one of them is kind of spelled funny to be exact, or if you want to emphasize that you're putting all your non-radical factors in the front to prevent any kind of smeared reading errors. So try out some problems like those and let me know if you have any questions. And other than that, calculator.